Okay, so today our speaker is Dimitar Guelev, the head of our department, and he will talk about an application of separation in discrete time interval temporal logic to branching time. Please, Mitko.
Thank you. So actually, this talk is with some small results which are corollaries of what I deem to be a more important thing, and I talked about this in December. I mean a variant of the separation theorem for interval-based temporal logic, which is on the model of a celebrated theorem by Gabay for point-based temporal logic. And what I will do today is one result which is a direct application of this theorem, and one more result which is about the same system where that application occurs, but it's sort of independent, but it's relevant for the study of the system, which because of the first result can be regarded as, you know, getting a little more interesting as such. So I would actually spend most of the talk on extensive preliminaries, because I know that most of the audience is not doing this particular topic. So I'd rather not allow myself to feel comfortable for talking things which are bound not to be understood. I would do a self-contained talk instead. And here is the plan. So I will explain a little bit about, so briefly introduce all the systems that are involved, and then actually it will be very easy for me to, in a very short statement, I will do the result itself. Okay, so I start with the propositional linear temporal logic with past, which is the commonest temporal logic used in verification. It's an extension of just classical propositional logic, where instead of just a single word where things can be true or false, we have sequences of states. So you can think of some subinterval of the set of the integers, and for each time point from this interval, there is a set of atomic propositions which are regarded as true at that point. These are the models. These are the models. And the language has, along with the classical propositional logic connectives, it has two temporal connectives for the future and two temporal connectives for the past. So to evaluate a formula, it takes such a sequence and a distinguished position in it. And for instance, this formula, which is read next A, holds at position K if A itself holds at the position which follows K. The mirror image of next to the past is written like that, same symbol, but with a minus sign in it. And this holds for A if A itself holds in the previous position. And there are two binary temporal connectives, until and since, which are mirror to each other either. So A until B holds if B holds some number of steps away into the future, and A holds at all the steps starting from the reference one up to the one immediately before the step at which B holds. Yeah. Step or position, if you wish. And since it's the past mirror image of this thing, with everything happening into the past relative to the reference time point. Now, I will refer to this theorem later, but I can only reformulate this classical theorem at this point about LTL. Interestingly, in in this syntax, we can arbitrarily mix the use of past and future connectives. But in 1989, Gabay proved that this is not necessary for the full expressive power of the logic to be achieved. That is, if we forbid using the future constructs in the scope, that is as subformulas of the past constructs and vice versa, then we would obtain a class of formulas which are Boolean combinations of just past formulas with only the past constructs, and just future formulas with only the future constructs, and possibly some atomic propositions which are not in the scope of any construct, any temporal construct. If we do this, we still can express the same set of properties as we can with arbitrary formulas, with the nesting. That is, this is code separation. Now, on the whole, there are very good characterizations of the expressive power of linear temporal logic. Every unary predicate on sequences of states, such as what I described as the models of LTL, which is written in terms of a vocabulary of unary predicates. Yeah. These unary predicates correspond to the interpretation we have for atomic propositions. Every first order definable unary predicates in such a vocabulary can be written, can be expressed by an LTL formula. Now, if in the predicate language, recall that in the predicate language, we can use individual variables as parameters of these predicate symbols, quantification over them, etc., etc. In the temporal language, instead of quantification, we have this rather special looking constructs. Yeah. And it turns out that everything that we can write in the predicate language can be fit into the expressive power of this construct. So LTL has the expressive power of the first order monadic first order theory of the ordering of the natural numbers. Now, if we add quantification over propositions, recall that LTL propositional variables correspond to unary predicates in the first order language. If we allow quantification, then it's trivial to observe that we increase the expressive power of LTL to the monadic second order theory of the linear order of the natural numbers. Yeah. Now, another very important logic, computation tree logic, CTL, with a star. I'm not going to explain why the star is here. Yeah. I'm just going to talk about the system. Again, very commonly used for verifying temporal properties, except that another view of the modeling of time is subscribed to. Instead of having just a single timeline, we look at so-called Cryptic models, which are relational systems, essentially. It's that we have a set of states, one distinguished state, which is called initial. Sometimes people allow for a subset of the states to be all called initial, and a binary relation, which represents the passage of time, transitions, and a valuation relation, which links states and atomic propositions. So V holds for some atomic proposition on the state if that atomic proposition is regarded as true, as being true at that state. Now, a single Cryptic model enables the representation of not just one timeline. It can have encode possibly infinitely many behaviors in it. So if we want to talk about temporal properties, we have to be able to, of course, go to these behaviors, select these behaviors. So given a sequence of states, W, this set is the set of all the infinite runs in the given Cryptic model, which start as W. Roughly speaking, their first few states are the way W specifies, and each two successive states in this infinite sequence are linked by the transition relation for the passage of time. So actually, by this set, I denote all the infinite runs which are continuations of W. So if W is just the initial state, then this is the set of all the infinite runs in this model. All the infinite chains of states which are linked by the transition relation. And the respective sets of finite states are defined similarly. And again, we are interested in introducing, in having propositional quantification in CTL star. And for this purpose, we need to be able to write the modification of a model by changing the valuation of some atomic proposition so that it holds at some given set of states X. So here is the definition. This is known. Now this is just the semantics of CTL star. I have not talked about the meaning yet, and I'll ask you to endure one more slide of semantics before telling you how the meaning of what the syntax of CTL formulas is, and to how their meaning is defined. Now it turns out that in order to conveniently define the meaning of branching time formulas, we also have to look at so-called unwindings of Cryptic models. So what is the unwinding of a Cryptic model? Well, suppose that this is some arbitrary Cryptic model. This is the notation for its unwinding. In the unwound model, the states are the finite runs in the original model. So every finite run from the given model counts as a single state in the unwound model. And obviously this state contains all the information about how it was reached, roughly speaking, because it encodes the entire run which led to that state from the initial one. So the initial state of the unwound model is, of course, just a single state run from the original model. And the transition relation here actually says that moving from one state to another, that is moving from one finite run of the original model to another finite run of the original model. Both of these finite runs have the status of states in the unwound model, amounts to adding just one more state, making one more step. So V is a successor state of W if V is the extension of W by its last state. And the valuation is inherited from the given model. So the assignment of the atomic proposition at a finite run is the assignment of the atomic proposition according to the original model at the last state of this finite run. So actually runs in the unwound model.
May I a quick question?
Yeah.
Between 5 and 6, if you could switch back to 5 quickly to be able to continue in more sense.
Yeah,
so here the infinite runs.
Yeah.
So where does this statement on the right hand side expresses the infiniteness? In W or
here?
Okay.
And
But
this
the
is
formula,
finite.
okay.
Yeah.
It's a function. So W can be infinite.
Well, so this W is finite, and we are here defining the set of its infinite continuations. So you can see the first W
minus 1
states of the infinite continuations are S in W, but actually we are defining the set of the V's, which are infinite themselves. Yeah.
Okay, so actually K shows up that it's infinite.
K is
in
a
the statement
parameter.
itself.
Yeah, so this one consists of all the infinite extensions of a finite run.
Okay, now I got it.
Yeah.
Okay.
Thanks. Okay. So in the unwound model, actually runs, if you look at a run, finite or infinite run in the original model, it corresponds to a run in the unwound model. And this run actually consists of all the prefixes of the original one. Yeah. Just the initial state, then just the initial state with one more state, two more states, etc. And if you look at the unwound model and the original model, their sets of finite runs are isomorphic, even respecting the valuation. Their sets of infinite runs are isomorphic. If you apply unwinding twice, you get an isomorphic model already. But there are nice things which are valuable, and this is why we want unwinding in our picture. So the nice things originate from the fact that in the unwound model, every state is the last state of a unique run, yeah, which is indeed encoded in it. And even more important, if we choose to consider varying the assignment of an atomic proposition, in the unwound model, the atomic proposition may have different values at states which, roughly speaking, originate from the same original model state. You know, if the original model loops, if it visits a certain state several times, then it will have to have the same value there for all the atomic propositions. But here, by choosing X to vary over all the subsets of the unwound models states, we can allow them to these values to be different. So this affects the meaning of quantification. Now I go to the syntax and the semantics of CTL now that I have already discussed the structures involved. So CTL star is an extension of LTL. It has the classical propositional connectives. It has the linear temporal connectives of LTL, and it has the most distinctive thing of CTL is the path quantifier. Here, this looks like a quantifier, but you can see that there is no variable written in the middle. So the meaning of all the constructs which are inherited from classical propositional logic and linear time is just like in LTL. You know, the form of the satisfaction relation involves the model, some infinite run in it, and the position in that infinite run. And actually, the semantics of these linear time connectives, it's defined just like in LTL with respect to this particular infinite run and the position in it. The CTL specific construct, the path quantifier, is defined in the following way. So given some infinite run and the position in it in the model, exists A holds if there exists some possibly different infinite run which satisfies A at the same position. And that run is supposed to be the same as W up to this position. From that point, it may differ. So it has to be one of the continuations of the prefix of W up to position K. From that point, it may be the same or different from W. Roughly speaking, this means that from position K, there is a branch from W, so that taking this branch would give us a run satisfying K. Yeah. So this allows us to say in CTL that some development is possible together with other developments, because it's possible that both exists A and the negation of A hold at the same run until the same position. And propositional quantification is defined as expected, except that before saying that A is supposed to hold for a suitable set of states, being the assignment of P, we move from the given model to its unwinding. Which allows us to vary the assignment of P along the runs in the unwinding, so that P has different values at states which originate from the same state from the original model. Now, of course, CTL star subsumes LTL for obvious reasons. And CTL star with this definition of the propositional quantification also subsumes propositionally quantified LTL. Now, why is this interesting? Well, I want to highlight a particular interesting application of propositionally quantified CTL star. An application to the reasoning of about strategic ability. Now, strategic ability has yet another type of structures being used for reasoning about it. They are very much like Cryptic Models. However, instead of a transition relation for the passage of time, they have something a little more complicated. Recall that when reasoning about strategic ability, we have to take in account that there is some set of agents, some set of players. And in concurrent games models, which are used for this purpose, every agent has a set of actions. Every player has a set of actions. And instead of the transition relation, there is a so-called outcome function, which, given the current state in the model and the vector of actions, one action for each player, calculates the next state. So what is encoded in the outcome function is what happens in each particular state when each of the players chooses an action, and then this vector of action is simultaneously implemented to determine the next state. And strategic ability is about the existence of strategies for achieving things. Yeah. So what is a strategy? Well, a strategy is a function. A strategy for player I is a function which tells player I, given a finite run, given what's already happened along a play so far, what its next action is supposed to be. Now, there exist dedicated logical notations for concurrent game models and for reasoning about strategic ability on concurrent game models, but CTL can be used too, and indeed it is recognized as an intermediate language for such reasoning, because it admits translations of the more dedicated, the more specialized notations into it. And furthermore, it has decidable validity and decidable model checking, which means that it's just as good, except for the lack of a very dedicated syntax. So, of course, CTL star requires a cryptic model, not this thing here. But we can define a cryptic model using the outcome function like that. So two states are related by the passage of time if some vector of actions causes one of them to become the other. And if we take an arbitrary concurrent game model and use this equivalence to define a transition relation on it, we get a cryptic model where we can interpret CTL star. So one more thing that is there that we need in order to get CTL star to be useful. We need to have a dedicated part of the vocabulary in our model so that we can identify actions. How do we do this? Well, upon unraveling the model, recall that upon unraveling the model, we store all the history of all the previous states that led to some particular state in that state, roughly speaking, because we move from just abstract states to states which are sequences, including the actually entire finite place. Yeah. So upon unraveling a model, we can, along with storing the past, we can also include information about the latest step that was taken in the hypothetical play which led to some particular state. So if we have, say, this finite run in the original concurrent game model, this says that from the initial state, this vector of action was chosen, then this state was achieved, which was the outcome. Then another vector of action was chosen, then this state was achieved as the outcome, etc. So from this finite run, we built a state in the unraveled model, which, along with including the sequence of states from the finite run, also stores the last action, a vector of actions. Yeah. And then we add all the names of the actions for the various agents to our vocabulary. And we extend the valuation relation as follows. For atomic propositions which come from the original vocabulary, it's in the usual way. For atomic propositions which denote actions in a state which is actually a finite run, such an atomic proposition holds if for atomic propositions which stand for actions of player I, the ith, the component of the last action vector stored in this space, which took place along this finite run, was this given action. Yeah. So this means that with this atomic proposition, we can test what was the last action which took place, so that we got to the state representing this particular finite run, yeah, in the unwinding. And of course, at the initial state, we have no previous action. Therefore, we allow an asterisk to fill in this position here, yeah. Just indicating no previous action. Now having this notation, we can make the crucial step that enables QCTL to be used for reasoning about strategic ability. Now think of some subset of the players. And suppose that we have a strategy for each of them. So this is a strategy profile for the set of players gamma. Given that, in the unwound model, given that strategy profile, we can define the set of states which can be reached by runs in which the latest action is according to this strategy profile. Actually, this strategy profile does not include necessarily all the agents, all the players. But all that we require is that as far as these players are concerned, the action that was taken was according to the strategy. The other players may have played whatever they wished. Now look at this formula, very simple CTL star formula. It says that its parameter atomic proposition holds in those successor state of the reference state where some particular vector of actions was the last action to be taken. So let me read it more carefully once again. So given a vector of actions with one action in it for each member of gamma, the set of our players, hat A, given hat A stands for the conjunction of all of its components, which are also atomic propositions. Now, what this formula says is that there is, for the current state, there is some particular such vector, such that in the states one step away into the future, S holds only if these states were reached by this particular actions by the members of gamma, and possibly some unspecified actions by other players. Now, it can be easily realized that using this formula, we can write this formula which constrains the atomic proposition S to range over sets of this form. Sets of states which are reachable by following a particular strategy profile on behalf of the members of gamma. Now we can easily write down what it means for gamma to be able to enforce some development of the game. This means that there exists an S such that S represents the states which are reachable when the members of gamma follow some strategy, no matter what. And here the existential quantifier guarantees us that S would range over those states for all the strategies that gamma may have, all the strategy profiles. And there exists such a strategy such that if we are along a run which is entirely built of states where the strategy is followed, then this run should also satisfy the condition A. So informally, this can be read as gamma. There is a strategy profile for gamma. There is an S, which happens to stand for a strategy profile for gamma, such that if gamma follows S, then A holds. And this is the basic construct of the most popular group of logics for strategic ability. There is dedicated notation there. Now I'm moving to the motivation. So I'm already in a position to give the motivation for my study. Now, how about writing these conditions, writing things about strategic ability, writing things about other things that we can write in CTL star, but with interval-based conditions A, instead of the point-based ones, which we have if we are using LTL as the linear time subset of the language. Yeah. Why is this good? Well, interval temporal logic that I'm going to talk about next is more expressive than LTL. It does not require propositional quantification in order to achieve second or the expressive power of monadic second order theory. Maybe this is not convincing enough because actually there are plenty of notations in the literature, both logics and automata based, where this expressive power is achieved. But if we choose an interval-based language, the one that I'm going to explain next, it's not a contribution, the language itself, but the results about it are. We have some other benefits. Because of the particular choice of the ITL connectives, they are compositional, and they facilitate something that is called big step reasoning in theoretical informatics, computer science, and also contract-based reasoning because of the compositionality. Okay. So why not do this? Well, what is interval temporal logic? Semantics, the structures are just like in LTL, except that instead of taking a timeline and one reference position in it in order to interpret a formula, we take two. Therefore, this way we focus on sub-interval from this timeline, namely the states from position I to position J, when determining whether a condition is true or not. So J here may be omega as well. I is bound to be finite, but J may equal omega. And we have an altogether different set of connectives because of looking at intervals. We have a next time operator again. However, in LTL, we are actually always looking at the infinite interval starting from the only reference position we have. We don't have J, it's always implicitly assumed to be infinity. So our next time operator here moves us from this interval to an interval which is obtained by cutting off the first state. So we move one state into the future. And very importantly, we have, this is actually the most interesting operator, we have an operator for modeling sequential composition. Interval ij satisfies the sequential composition, the chop of A and B, if it can be partitioned with an intermediate position, so that the first part satisfies A and the second part satisfies B. And we also have Kleene star, which accounts for some finite or infinite partitioning of the reference interval into subintervals, each of them satisfying the operand A. So this is ITL. Now, based on this system, which is actually linear time, where models are just a single timeline, we can define a branching time system, a computation tree logic. Again, everything that refers to a single timeline is inherited from ITL. And we have almost the same, well, almost up to just having this additional reference point, the same in meaning of the path quantifier as well. Now how about writing properties in this logic? Well, interestingly, the literature already has ITLs. These are dedicated notations for strategic ability, which subsume this system. But these systems on their turn are subsumed by the extension of what's here by propositional quantification. And next time to address questions which have not been covered in these ITLs, interval-based ITLs. Yeah. Now, first question to do. Observe that the ITL connectives are all introspective. What this means is that given an interval with the endpoints being at positions I and j in the timeline, by using these connectives, we can refer only to subintervals of this interval. Here, from ij, we move to the subinterval I plus 1j, which is the same, but with the I position clipped off. Chop also allows reference to from ij to some subintervals of it. Yeah. Same with the with chop star, the clean star analog. So the basic system of ITL does not include what the past temporal operators provide in LTL. Now, in the literature, there are systems where this is included, and let's put these the two of the operators from those systems in ITL2. So let's look at the neighborhood modalities. So these are two unary operators which allow reference to adjacent intervals into the past and into the future, respectively, of the reference interval. If the reference interval is ij, the diamond LAA holds provided that there is some interval on the left of ij where the operand itself holds. So I is the beginning point of the reference interval, and here we want an interval whose endpoint is I and whose beginning point is somewhere in the past. The diamond R modality does the same thing about the future. Diamond R A holds if A itself holds at an interval which starts where the reference one ends and ends somewhere in the future. It may as well be an infinite one. Now, why are these neighborhood modalities valuable? And of course, they are in the literature in systems of interval-based logic, but not this particular one. Well, because it's convenient, at least for one thing, it's convenient to be able to refer to the past. So if I want to express properties, it may be a lot more concise for me to be able to write that, say, something happened somewhere in the beginning of time. The initial parameter values of some parameters were such and such, and I'd like to be able to do this in formulas which are evaluated at intervals in the future, instead of just for this purpose having to go for formulas which are only evaluated at initial intervals starting from the beginning. So this gives a lot of convenience. Yeah, and there is a lot of work in the literature on how to handle past operators in the point-based setting. So it turns out that adding the neighborhood modalities can be done in no cost to ITL. So this is one of the results that I'm present today. This is an immediate corollary of the availability of a separation theorem for ITL. Just like in LTL, we can restrict the use, we can, in the extension of ITL by these two neighborhood modalities, we can restrict the use of future constructs in the, so future, by future I means formulas using this modality in the scope of past construct, that is constructs using this modality. So we can partition, we can define three subsets of the set of the formulas of ITL with the modalities. One is the set of the introspective formulas, which are formulas built only using the introspective connectives of ITL that I already mentioned. That is the entire ITL without the extending operators. We can also define the set of the future formulas and the set of the past formulas. So future formulas include introspective formulas and allow the use of the right neighborhood modality, which is for the future, but not the left neighborhood modality. Similarly, past formulas exclude the right neighborhood modality. So separation in ITL states that every ITL formula is equivalent to a Boolean combination of future and past formulas. And this is here written in a somewhat stronger form. Indeed, we can additionally restrict the syntax to have Boolean combinations of so-called strictly future and strictly past formulas and introspective formulas. Now, I'm not going to do the details of this, but strictly future and strictly past formulas, they have this syntax where F is future and past respectively. They additionally are restricted by virtue of their syntax not to be imposing conditions on the endpoints of the reference interval to which their operands are to which the adjacent intervals are used for evaluating their operands. Now, by this theorem, using this theorem, it turns out that we can eliminate the use of neighborhood modalities in ICTL. What do I mean? In the branching time temporal logic ICTL, if we add the neighborhood modalities into it, then for any formula in this logic with the unrestricted use of the neighborhood modalities in it, there exists another formula which does not have them at all, and which is such that on infinite initial runs, the two formulas are equivalent. Which means that if we want to specify properties, we can freely use the neighborhood modalities, but our algorithms for deciding validity, model checking, etc., need only work for formulas in the basic language without these modalities for everything to be possible to handle. We do not need to extend those basic algorithms as well. Okay. Now, another thing about ICTL, which is not an application of the separation theorem, but it's much too relevant for me not to include in the talk. Yeah. I mentioned that propositional quantification is expressible in ITL. ITL is the underlying linear time logic of ICTL. And we can straightforwardly define propositional quantification in ICTL. And indeed, it's instrumental in the expressing of strategic ability and possibly many other things in ICTL. So it's important to look at this extension of ICTL with propositional quantification. Now, in point-based LTL, which is the underlying temporal logic of point-based CTL star, propositional quantification is not expressible. Propositionally quantified LTL is a stronger system than just LTL. For ITL, this is not the case. Propositionally quantified ITL is the same in terms of expressive power as just ITL. It turns out that this holds for ICTL as well. And this is a new result. Yeah. So any ICTL formula with propositional quantification is equivalent to a quantifier-free ICTL formula. And interestingly, this leads to a decision procedure for validity in ICTL, because a formula is always equivalent. So the validity of a formula is equivalent to the validity of its universal closure. But if we can eliminate quantifiers, then this universal closure is actually equivalent to a quantifier-free formula, but this quantifier-free formula is bound to have no atomic propositions either. So it turns out that by quantifier elimination, I can transform any ICTL formula into an ICTL formula where the only atomic proposition is logical falsehood. And such formulas are trivial to check for validity. Yeah. Now, nothing like this is there for point-based propositionally quantified CTL star. There is a highly non-trivial theory due to French. Actually, his contribution is very important for the usability of propositionally quantified CTL star at all, because he proved that validity is decidable for propositionally quantified CTL star. But it was a lot of work, nothing as trivial looking as this. Yeah. Of course, the proof of this theorem is not really trivial, but nothing like a PhD thesis such as that of Tim French. So just to recap, so here is a comparisons of the related results, points with point-based quantifier, propositionally quantified CTL star. First, we have elimination of the neighborhood modalities. This is totally analogous to the elimination of the past, which is available for point-based logics thanks to Gabai's original separation theorem. Now, as I said, propositional quantifiers cannot be eliminated in LTL and CTL star. There is a dedicated different theory for the systems with the quantifiers. Now, what are the gains? Well, ITL's connectives have another opportunity to prove themselves. That is we can use the compositionality of these connectives to reason about abstraction, contract-based, to do contract-based reasoning, etc. So compared to the ITL's connectives, in practical terms, LTL is very low level, because in LTL, everything has to be done, written, expressed in terms of step-by-step, small step, one state at a time transitions. And the possibility to eliminate, to use the past for free and propositional quantification can be enjoyed, as I said. Okay, so that's all. Thank you. Thank you for your attention.
Thank you very much for the nice talk. Do we have any questions or comments?
Maybe I can ask something.
Okay, yes, sure.
So, Mitko, I think what you have presented has actually very important direct application to natural language. But just as it is, if you go back to probably it first to start with, it was 17, 18 page before the possibility for elimination of the predicate quantification. Maybe here, yes. So actually, maybe back, yes, introspect, maybe one page back. Yes, here. So interval-based presentation here, logic, they have direct application to express certain special case, the way I see it, special case aspects expressed, for example, in English, in Bulgarian also, but in Bulgarian aspects are very complicated, but English, they're quite simple. And here you can directly represent for example, the present perfect aspect, even time, because the two are a little bit different. But the special case where you have definitely for verbs in passive form, where it is known that the action has been happening all the time, because here the formula says that the formula 1, 2, 3, and 4. So here these formulas are telling that they are true in all the points in the interval, right?
You can define such a construct, but I have not put it here. So here is, roughly speaking, if you say, if you use chop,
yeah,
and set the first operand to true,
yeah,
you're essentially saying that there is a suffix satisfying B.
Yeah.
And if you take the universal dual, then you say that all the suffixes satisfy B. So this is the universal, the box abbreviation in ITL. I'm thinking of, maybe you are thinking of this.
Yes, this one has direct application to represent the logical forms of special class of passive forms. But for other more broader class of passive representations, then you need to somehow say that there is a finite subset of this between like K, not for all K, but for finite subset of Ks where this happened. These formulas are true. Then you extend by adding one more possible chop here. Then you cover also the broader class of passive forms. And it's important to the database applications, because then you switch. Usually database can be contributed by different sources, but a significant portion can be contributed by natural language. And then you immediately have direct application for transfers from natural language expressions, having this present perfect, and then even for the future and for the past perfects. But one starts with the present perfect. So B will be something that now, and in between there were separated points where that happened. It doesn't need to be all through the whole interval. So it will be something like points inside of the interval, not necessarily the entire.
I got you.
And then it has direct application. So then actually, with respect to the logic, you can Montague grammar to start with. Montague, not grammar, but intentional logic, forgetting about the natural language, just his intentional logic. It is a model logic and it's higher order. But then if you can directly extend a subclass of his model logic that apply only to the propositional part without predicate, which means that the database will consist only on atomic formulas without predicate and variables about individuals, etc., etc. And then the next step after you extend, you get such intentional logic only for your part, for temporal logics with intervals, and with this extended point, especially, but just even without the points, just the way as it is, you can try to find a subclass of limited Montague intentional logic only to the propositional, to propositional intentional logic. And then using Gaussian logic, if you go back to the so here the syntax has only propositional variables. But if you add also variables for states and for points, depending how you define the states, you can define the states, W, etc., in such a way as a tuple so that you have points in time, or then you can define intervals, and then actually your logic has direct application also to his logic, because his logic.
Just a comment, Rusanka, this is not a logic I invented. I mean, interval temporal logic is been there since the 80s.
Yes, go now. Yeah, I start.
Because you said my logic, it's not. Yeah.
Well, I continue now. So up to here, whoever invented it, temporal logic, and I have been telling you because I think that you can do it. So then, again, the first step is to define possibly, but even alternatively without it, the point-wise, within a given interval, the point-wise, what was it, A, comma, 8 semicolon B's cut or what, chops or whatever, the intervals. So you have to, you can extend as it is by adding finite, because you are working with the integers, right? So within integers, interval defined by integer numbers, then you can define finite number points in an interval corresponding formula to this one. And then let's go to the next one, where it is where you have quantifier free variant. So up to here, you have two possibilities for extensions.
This one?
Interval-based, yes. Let me see. Yes, here. This one also, just as it is, can be used, can be compared, firstly, to a special only with propositional variables in Montague intentional logic. And one more step, if you add also variables for states and points, possibly, because you can define the states as a tuple with agents and points. And then it's a very, there is a way, technique to define relations, to express points by using just states. Then you can define from here, interval-based. Here you can also two levels of extensions without any variables for states, just as it is, by adding only finite chops with respect to the inside of interval, another one formula, then you can express a very nice subset of Montague intentional logic. But if you add state variables, then it's a next extension to Gaussian intentional logic, only propositional part. And then next point. Where is the theorem of 15 and 16? So these are levels of extensions. Okay, before the previous page, 16 or 7. Yeah, oh, you call those skips. So now this one also, that's the next level of special subpart of Montague intentional logic. And there it's very interesting. As it is to me, it looks like that you will define a special subset of Montague intentional logic representable by this logic. Only that. And then the next step is for the same for Gaussian. For Gaussian is very valuable. Both are valuable, but Montague itself is already old-fashioned, according to me. Gaussian is more flexible with respect to the natural language. At least in Reinhard Mushkin, he proved that in his dissertation and subsequent work, and I myself have proved that for Muscovakis. So for Muscovakis also it applies, but then you will need much more work here for this logic. It will be much more. So the best way is one to start with subpart of Montague intentional logic and Gaussian. They may not really be proper inclusion, but it will include a significant portion of propositional Montague intentional logic without going to the higher order. And then also the quantifier, the next theorem, what was it? So did you get me what I suggest here for your
I hope so. Yeah, so it was a comment, no question, yes?
Yes. So yeah. For Gaussian, yeah. So, why Gaussian? In Montague, you have the model formulas that you have them. Mm. You can add false. He doesn't have false, but you can add it very easily, no problem. He also likes all possible logical connections. You can work only with false and implication, no problem.
Then, I just want to have a minimal set, just in order.
Yes, for applications to direct applications to natural language semantics, the general view is it's good, very important result to express such subset. For example, I see new in Haskell, that's important, for example. But Haskell is also, programming language is also higher order. But it's good for people, community working computational semantics, to see all the logical connections. Directly, you can call them abbreviations, for example. At the beginning, you introduce them as abbreviations, conjunction, disjunction. And then the next one, the quantifier free result is very important too. So then you will apply very directly the results here for a special special domain limited database and to special domain limited semantics of natural language. And that's valuable because computational semantics of human language is extraordinarily complicated. So the best application is when you find to computational semantics of natural languages to find a specific case, domain limited, for example, in medical documentations or in administrative documentations of the government or whatever administration. So there, they fill up forms already online in natural language, and that natural language is very easy to express in limited logic like yours, only propositional, without going to the predicate. And that's what people need. The technology right now needs very directly. And people are actually doing that. even if it's without being verified by mathematical logic, but you are providing foundations of those special case applications in special domains.
Rusanka, the main customers for these are people who design hardware. So Verilog, VHDL, they have languages for properties which have scores of dedicated derived constructs
Yes.
for that. Also, if you're familiar with the Java Pathfinder, the model checker, the Kansas State. So they had three basic systems of logic used. One was Interval Temporal Logic, and also I'm talking something about this was already there in the year 2000 or so. So, and they had also huge libraries of derived constructs to make it easier for their users to, use their favorite, how to say, grammar for writing temporal properties, not go to the basic connectives in the first place.
Yeah.
So the fundamental connectives. So these are, but they are again concerned with verifying Java programs. So yeah.
Yeah. So
yeah. Okay.
Even,
so this is where from I draw the. I mean, these are the applications I know about. Yeah. So what you're saying is new to me. Yeah. So
yes, it is very direct. Mm-hmm.
Yeah.
So you can trust me, and when you write a paper, just say it has applications to a special domain, to computational semantics of human language for special domains. Just the way I explained it, for example, the database will be translations from natural language, simple natural language is in medical databases in Europe, in America, I don't know in Bulgaria, but everywhere the world is moving into processing whatever the doctors write. They don't write full sentences, they write simple expressions, and you can translate them right away into your logic. So you provide very important application, just as it is. But if you find a connection with a special subset or subclass, special limited Montague intentional logic, then it has in well-established computational semantics for natural language, and then Galen also, and then Muscovakis, but Muscovakis, you'll need more work. For Galen, you need to add here definitely variables for states. And then with Galen, you will have go back here where, yeah, but even here, just you see the future formula. So in Galen, you can manage past and future without model operators, but you can keep the model operators because you will have variables for states, but then you can add quantifiers over variables or states. That's the way is the link between the model operator and extended intentional logic, Galen intentional logic, and Reinhardt, etc., and mine too. So then I don't know what will be the result because you have quantified formulas inside of the language. What will be here like this one in the next theorem, because you are getting rid of the quantifiers. How you are going to get rid of the quantifiers in such Galen, a la Galen interval temporal logic is more complicated. If you keep the model operator, you'll manage very easily.
Okay, do we have more questions or comments? If not, let's thank the speaker for the nice talk.
Thank you very much. It was very nice.
Thank you all. Thank you for your attention. I will now stop recording.